Okay, so now that we have calculated mean or expected value for these weighted random variables, let's take a look at variance and standard deviation for them. Because if we're using mean for our measure of the center, then we're going to use standard deviation for our measure of the spread. Okay? Remember, if we use median for this measure of the center, then we're using IQR things. If we use mean, we're using standard deviation for our spread. So same with our mean here, we need to take into account that these have weighted values. Remember, our variance is basically just a square of the deviations. Okay, I know that, so these are our formulas, and they're super crazy looking, and remember, you're not going to have to use the formulas in the sense that you have to actually calculate it from the formula. You know, your calculator will do standard deviation for you, and it will pull the variance for you. But if you are asked for this, you have to show your work. So you do need to know what formula to go look for so that you can plug in your values into your formula. So let's look at what we're using here when we do these formulas here. So our x1, x2, x3, these are our various values. Remember, when we see in our formulas here, we see this little xi. Basically, that means all the values. So, for instance, in the standard deviation formula here, when you are looking at the square root of the sum of xi minus the expected value squared times the probabilities of all of those, okay, that means we're going to do this formula right here for every value that we have. Okay, so let's look back up. And then our probabilities, we're going to multiply it for our probabilities each time. You can see this here in this pulled out variance formula. If you just look right here at this first part, the x1 value minus the mean or the expected value squared times the probability of value number 1, right? So using that information right here. And then the same for 2, right? We take value 2, subtract the mean from it, square it, multiply by the probability. And then the only thing different when we do standard deviation now is we need to get rid of those squares. We need to take that square root of it. Okay, so let's look at how we are going to do this, how we could show our work for this, as well as how our calculator can show us how to do this. Okay, so in this example here, you've calculated an APGAR score. That's basically a basic health score for babies when they're born, of a randomly chosen newborn, and you calculated the expected value, which is the 8.128, so that's our expected value of our mean. The table gives us our probability distribution one more time. So this kind of table right here is called our probability distribution. It shows the distributions of the different probabilities. Newborns can only score 0, 1, 2, 3, and up to a 10. They can't score like a 4.2 or a 5.7. And then this shows the distribution of those various probabilities of those scores. And so that's our probability distribution. So we're asked here to compute and interpret the standard deviation of the random variable here. So to show our work for this here, we're only doing standard deviation. So to show our work for this, we can go ahead and we can calculate the variance. Okay, and remember, we don't have to do it for all of them, right? 1 minus 8.28 squared times the probability of 0, which is 0.001, plus, 1 minus 8.128 times the probability of, squared, times the probability of 1, 0.006, plus, and let's do our ... And then we've got our last one there, right? Our 10 minus 8.128 squared times 0.053. So that's enough for showing your work. And so that would get you your variance, which is 2.066. And then to calculate my standard deviation of that, my standard deviation is just going to be the square root of 2.066, which is going to equal 1.437. But we're not done because it asks you to compute and interpret. So you are not done because you have not interpreted the standard deviation here. So think back to our sentences that we had for this before. It still means the same thing, that it's our typical distance from the mean. So the standard deviation is 1.437. And so a randomly selected baby's APGAR score will be different from the mean, or will typically differ from the mean of 8.128 by about 1.4 units. Okay, so again, this tells us our typical distance from the mean on a randomly selected baby. And again, that's the same as it was before. Okay, and so to plug this into the calculator, that will also be the same as it was before. You will go ahead and you will enter the values into list 1. So the values will go into list 1. List 1 is your values, and list 2 will be your probabilities. So when you put those in to list 1 and list 2 with your values and your probabilities, you can pull histograms of that information. You can you could draw basically any kind of graph you wanted on your calculator with that information. You can also do your 1-var stats. Right? We can also do our 1-var stats, and we can go ahead and it will give us the standard deviation there. But again, remember, that won't count as full credit. You will need to have written out and shown your work there. So in an ideal world, you'll pause it, you'll go ahead and do 1 and 2, and then come back and restart it and check your work. So what we have here is a large auto dealership keeps track of sales made during each hour of the day. Let X equal the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of X is as follows. Compute and interpret the mean of X. So remember, when we're doing the mean of X here, we are, So to calculate that, we need to multiply each value of X times its probability, and then add them all together. This one isn't too long to bother with the ... part. Okay, and so when you do that, that should give you 1.1. So even though this is a discrete variable where you can't sell a fraction of a car, okay, with your mean, your averages, remember, you can. If you calculated 1.1 and you went ahead and you wrote that the mean equaled 1 because you think, well, it has to be one of these values, I can't sell a part of a car, okay, you will end up getting it wrong. Okay, so your mean or your average can be parts of the whole number. So what that means for our interpretation, right? It means that after many, many, many Fridays, so you can't forget that. Remember our context, right? So many, many, many Fridays are randomly selected. The average numbers of cars that will be sold will be 1.1. Remember, because this is probability, so we need to think on the long term, not on the short term. For number 2, we are computing and interpreting the standard deviation of X. Okay, so the standard deviation of X would be our variance of X here. Take the square root of the variance of X. So our variance of X would be 0 minus 1.1 squared times 0.3 plus, I'm going to go ahead and do my ... dots, even though it was a little too soon to do them. 3 minus 1.1 squared times 0.1, okay, which is going to give me 0.89. So my standard deviation then is going to be the square root of 0.89, which is 0.943. And hopefully you type that into your calculator, and that's the same thing you got from your calculator. And so then you need to do your interpretation. Remember, we need to interpret what this means. So the number of cars, your context, the number of cars sold on a randomly selected Friday will typically vary from the mean, which is 1.1, by about 0.943 cars. Okay, and we can do some interpretation statements for these sentence stems for these if you guys would like. So now that we've taken a look at discrete random variables, let's look at a continuous random variable. So a continuous random variable, this is all the values. A lot of times these are things that we measure, not things that we count. Like before, we counted how many cars were sold. This would be something like measuring height or measuring the length of those cars or the weight of those cars, okay? Where I could have something that weighs part of a pound or is part of an inch tall. So we're continuous in that sense. All the values in an interval of numbers, okay? Not just the whole number values. Okay? So all the values there in an interval of numbers. And we can use density curves. We can find, remember when we talked about this before, the area under the curve is equivalent to the probability there. So we can use a density curve to do that. This one's kind of a weird example. We'll do a normal example in just a minute. But I thought it would be beneficial for you to see this one, just to remember some of these. Okay, this is our density curve here. Remember, this has a uniform density. Okay, so the likelihood of it happening is the same. So there's a uniform density there. And so to find the area here, okay, we're basically just finding the area of that rectangle, which is a little easier than trying to find the area of like an awkwardly shaped curved triangle here. Okay, so in this uniform density curve here, okay, I'm going from 0.3 to 0.7. Okay, and so length times width, 0.4 times 1. So my area here is 0.4, so that's my probability there. And so basically what that states is the probability of whatever it is that you're looking for. So the probability of y being greater than or equal to 0.3 and less than or equal to 0.7. That's what that information shows us. Okay, so let's look at this example here using a normal curve. The heights of young women closely follow the normal distribution with mean of 64 inches and a standard deviation of 2.7 inches. This is a distribution for a large set of data. Now choose one young woman at random. Call her height y. If we repeat the random choice very many times, the distribution of values of y is the same normal distribution that describes the heights of all young women. Find the probability that the chosen woman is between 68 and 70 inches tall. What's the probability that a randomly chosen young woman has a height between 68 and 70 inches tall? So the first thing we need to do, remember, is we state what we're looking for. And so what we're looking for here is that we want a probability that is between 68 and 70 inches. Okay, we've drawn the curve over here. Remember, when you draw your curve, you need to make sure you label it. So we've drawn the curve, we labeled it, we've shaded the area of interest there. And so that shows, remember on that free response that we did, that covers the boundaries there too. So 68 to 70, that area is shaded, and we're looking for that particular probability there. So the first thing that we need to do when we show our work is we need to do two z-score calculations here. Okay, we need a z-score for 68 and we need a z-score, which is 1.48, and then we need a z-score for 70. So we go ahead and we find our z-scores, which is our, remember those standardized scores. So you could draw a picture. We could draw our standardized curve, right, where our mean is 0 and our standard deviation is 1, and that we'd still be in this same area out here, right, shading this. And this would be 2.22, and this would be 1.48. Okay, but that's part of that identifying that curve. Okay, let me get rid of that, free up some space. Okay, so we've got z-scores for both of those. Okay, and then you can go into table A, and you guys can do what y'all do best, okay, which is find the area in between. So you're looking for the probability here that we are at 1.48, and we've switched over to Z, right, because we're using table A and our Z scores, okay, which is equivalent to, remember your table A shows you, remember your tables show you your probability of things to the left, right? But I need to the left of one and to the right of the other. So I need to the left of my bigger value, right, that it's less than or equal to 2.22, but I need to the right of my smaller value. So I'm going to subtract the value I get of the lower boundary, okay, and I'm going to get 0.0562. Oops, I messed those up. You could also do this in your calculator. Okay, you could go into your calculator. You could go ahead and do your, you would still want to show your work for your Z-scores here, so you'd still want to show that. And you could go in and you could use those if you wanted to. You would do your normal CDF, and then your lower, you could have two things going on here. You could use your Z-scores, or you can use what's given to you. So your lower would be 68, your upper would be 70, your mean would be 64, and your standard deviation would be 2.7. And that should give you the same thing. You could also go in and you could put your 1.48 for your lower and your 2.22 for your upper, but that would make your mean 0 and your standard deviation 1. Remember, because you'd be using your standard curve. And then now that you've shown all your work and done your calculations, you need to actually answer the question. There's about a 5.6% chance that a randomly chosen young woman has a height between 68 and 70 inches. Okay, so putting it all in context and explaining what this 0.0562 means. That there's about a 5.6% chance that a randomly chosen young woman will have a height between those two values, between 68 and 70 inches. So we'll practice more with this in class and get this all down.